OK，那我们要给周洋一个让周洋拿他电脑嘛，这样的话他可以 share screen。OK， let me see. OK. Hi, we are starting now. Like, feel free to find a seat, and yeah, we'll start like in several minutes. Yeah, we're starting. We're starting. 哦，你好，不好意思，我们要开始了。好。哦。OK, test. Can you hear it from your phone? 哦 我们这个挺多次了，10多次了，但是就之前主要线上为主，这次是线下。对，主要是因为你可以来，之前谢谢。Yeah, hi. So I see people are like roughly ready here. So now let's start. Um, yeah. So today we are hosting an event like about large language model, AI infrastructure, and agents. And we invite one of our speakers here. Like here's Zhou Yang, and yeah, Zhou Yang is he's an assistant professor in UC Davis, and he was like he is now working on large language model related stuff, and especially on the communication layer. And also we have another speaker, but unfortunately he's not able to come today. So I will also like so we'll also like me myself from LMCache, I'm Kuntai, and I will also share some stuff about the large language model plus agent serving. And yeah, so basically our schedule will be first our guest speaker, Joanne, will give a talk first. And then feel free to ask any question if you have like any concerns. It will be on the networking layer, so it's a little bit technical, but it's very rewarding. Like it's very interesting about like the whole communication stack under the large language models. And then I will give several examples on the agent plus LLM. One, we will show a short demo, and also we will also share some technical contents. Okay, so yeah, sure. Let's start. Thank you.
Should I stand up?
You don't have to. Oh,
so how should I like check? Okay. Hello everyone. So my name is Yang, and you can just call me Yang, and no need to call anything else. So this is a project we have been working on since last year when I was doing a postdoc in the UC Berkeley. You will see in the page there are a lot of authors. They are from many different organizations. Tsinghua, UC Berkeley, IBM, AWS, Broadcom, and yeah, a lot of affiliations. And we're working on this something called a extensible software transport layer for GPU networking. It covers both LLM inference, LLM training, pre-training, whatever you can think of that happens inside the GPU communications. We want to make it faster and extensible and more flexible. Can you switch to the next slide? Okay. Let me just first give you a quick overview about what UCCL project is about. or you can also call it Uncle. It's another name. We want to build the fastest collective communication libraries, basic CCL, and we try to innovate on different layers. You can roughly think of there are 3 layers that we're currently working on. The top layer is on the ML applications. They use these our UCL collective libraries. You can think of right now people just use Nico, but we envision in the future we will get our own Nico that is faster than the existing Nico made by NVIDIA's or the Rico made by AMD. And in the middle layer, that is about this talk, that we're gonna re-architect the transport layer. This is what this talk is about. It tackles about the existing problems of the network transport layer in RDMA deployment, including their congestion control, load balancing, fault tolerance, routing, a lot of things. Beside this RDMA, we also cover many like non-RDMA NIC. How do you communicate over TCP faster? Or how do you communicate over NVLink faster? That's our second part of this work, and this is also this talk about. And in the bottom layer, we want to support heterogeneous vendors. You'll see we list the NVIDIA, AMD, Broadcom, IBM, AWS, and this will have already support all these vendors. For example, we can run on NVIDIA's GPUs, on AMD GPUs, on Broadcom's NIC. NIC means network interface card. That is the RDMA NIC. We can run IBM's non-RDMA NIC and also AWS RDMA NIC. And the project is open source. You can go there and to see if you can find something that might be useful to your work.
Sorry. So
okay.
Just want to the audience, can you briefly describe the impact of the project?
The impact. I say we support. Oh yeah, I think we support NVIDIA's AMD GPUs, both NVIDIA and AMDs. You can also run our prototype on Broadcom's RDMA NICs, not only and NVIDIA's RDMA NICs, of course, and also on the AWS EC2 using AWS build RDMA NICs. It can accelerate, especially for example on the AWS. I actually have a number here that improved by 33.3 higher throughput over the existing Nico by just innovating on the transport layer. We're also working with some companies like AMD, especially AMD, on their model trainings. How do we support this expert parallelism, especially large scale expert parallelism? How do we support the auto communication pattern more efficiently on AMD plus Broadcom NICs in their cluster? And also how we're gonna make AWS EFA work for this expert parallelism using something called IBGDA. That is another fancy word that I'll talk later. Yeah, we got some support from AWS. Yeah. Thanks. Yeah, thank you. Okay. I will first go through the motivation, 2 slides. It's about why we want to build something called extensible. By extensible, you normally can think of it, you can easily customize how this transport layer works for your application's needs. That's the definition of extensible or extensibility. We need extensibility because you see the ML workload, they are really fast evolving. 10 years ago, maybe you are using DN training that with even with some CPU-based parameter servers, or you just run some simple or reduce. Now, 5 years later, you see this training that we are using all kinds of collective communications. And then after 4 years, you do PD transfer, P2P transfer for PD disaggregation. And in the beginning of this year, probably the hottest thing is this something called DeepSeek V3 MOE. They're using expert parallelism that features really large scale auto communications. So they're really fast evolving. But if we go to next slides, you will see the network is actually slowly evolving. You might feel this might not be true because you see every year NVIDIA's put not every year, every probably 2 or 3 years, NVIDIA's double their NIC bandwidth. However, I'm going to tell you that their hardware control block on that RDMA NIC rarely changes. The reason because they're baked into the hardware ASIC logic. They're really time consuming to fabricate a new set of ASIC NICs. What they did is they just replicate that existing NIC into maybe two pieces, and they can get double performance. But still, they will hit some network problems. I will give you some very simple examples. What might be some network problems that impact your ML workload? You can see in this diagram, this is a typical data center network diagram. On the bottom part, there are 16 hosts. You can think of each host might have 8 GPUs. Internally, inside the host, they're connected through NVLink or XGMI on AMD GPUs. And the top 3 layers, they are all switches. And each line is a link. They're 400G link. It's a pretty typical industry setup. And these cards are really expensive. And however, think of you want to communicate from edge 5, one GPU from edge 5 to edge 10. That's the red curve, right? You will traverse some paths. You will traverse 3 layers because they cross. If you think of this as a rack switch or tall switch, it's an aggregate switch and core switch. The traverse is tall to this aggregate to this core switch. However, if you have another host like edge 6, send data to edge 12. If you are unfortunate, your path choose a left one. You will see that blue curve is actually conflicting with the red curve at actually 2 links. You can think of you can see the T3 to A3 and also A3 to C2. These 2 links are 400G, so they cannot sustain 2 400G traffic or flows. That will hit some network congestion. And of course, if you are lucky, your flow will traverse through this left curve like this. Then you do not have any shared link in the network layer. You will see nearly no network congestions or collisions, and you are good. So that's something we motivate us to think of why right now we are hitting these kind of network congestions. We also really severe network congestion. Not only me. If you go to the next slide, you will see many companies, they have solved these, they have seen these network problems. For example, the left case is from Meta. In their SICOM 24 paper, they mentioned the standard RDMA CC congestion control logic on the NIC DCQCN is not performance effective. They will aggressively drop their speed. They will limit itself to avoid any congestions in the network. So that created a lot of trouble for them. So what they did is they just disable it. And of course, if you're not a networking expert, you will know disabling CC is dangerous. If you, especially at this large scale, it can easily cause some deadlock or headline blocking, and many other things. Another example is from the Alibaba. They observed this flow collision I showed in the last slides because of the single pass nature of RDMA. What they did is they just rebuild everything about networking, so that which is costly to build and maintain. And finally, if you look at the deep EP MOE serving, they actually might have some network incast issues. But what they did right now is they just disable everything on the NIC and try to do it in the application level to avoid this kind of network problems. Okay, so the high-level takeaway from these slides is that we have a fast evolving ML workload, but the network hardware is actually slowly evolving. So we want to do something. So how could we do? If we go next slides. Yes. So the overarching problem we abstract into something called a network extensibility. By extensibility, I mean the ability to customize the network fabric, either your routing topology or congestion control logic, or the ways you do load balancing, so that you can customize them just for your applications, your production applications needs. So our approach is also very simple. We argue that you can do these things by burning a little bit CPU cores. That what we call a software-only approach, software-only extensible transport for GPU networking. So if you look at this big diagram, that shows a high-level overview of the current servers. They connect to another servers through these multiple paths. data center networks. As shown in the last slides, you will see they're multi-layer switches. They have different passes. They can have choice. In high level, what we did is we try to separate the real payload data that carries, for example, your LM training weights from the control headers that controls the transport layer behaviors. That's how we are then on the CPU side, we get that transport control data on the CPU 1 and 2. We can make customization based on the transport states we communicate between different GPUs or between different servers. So one important thing we did is we done some very many passes so that a big flow can be break into many small flows to avoid any potential network congestions. We have also done many fancier congestion control mechanism that is not available on the current hardware. We can also sustain like handling packet loss, which was really hard in the RDMA NIC because of NIC's limited memory. But now, because we do everything in the software, we can handle that. Okay, cool. Yeah, that's the overall picture. But of course, we need to solve two challenges. The first is how we can get this kind of decoupling between the data paths. You can think of data paths that transfer data between GPUs, and also the control paths that transfer some very small metadata between CPUs. How we can decouple that, especially make it work for existing RDMA NICs. There are many RDMA NICs. If you look at all these vendors have their own RDMA NICs. And of course, if we do a software solution, the second challenge is, can we achieve hardware level performance, even we're doing some software control paths? For example, if you look at the right nowadays, you have 3.2 terabits inter-server bandwidth, which is really crazy if you look at the number, because when I was doing my first year PhD, at that time, the fastest NIC is only 100 gigabits. So right now we have 32 times this increase on the NIC bandwidth. How can we handle that in CPU for the control path? So that's the two key challenges we try to solve in this work. Before that, any questions so far? Okay, guess we can go to the next slide. Okay, this might be a little bit technical, but the key idea is that there is some RDMA primitives that give you the abilities of separate these two parts. If you look at, there's a primitive called write with immediate number verb. Verb is basic RDMA operation. You call it a verb. You can just let the source CPU specify a 4-byte immediate data, and then specify the GPU address. Then the NIC will deserialize the packet into the data into packets and send over the network. You will see we have two parts. One is the control header embedded in this immediate data, including like connection IDs and also some chunk IDs that will be used to control how these chunks of data get transmitted. And also the green curve, the green curve is a data payload. And together they will be merged by the NIC and sent to the destination NIC as individual packets. So with this, we can kind of separate and make some controls on how we gonna do for our data that get transmitted over network. So one application we explore is, as you see before, if you have a very like a big single RDMA flows, you will hit some RDMA congestion very likely. What we did is we try to break that single flow into many small flows. Specifically, if you look at our implementation right now, for each connection between two GPUs, we will use actually 256 queue pairs. And we use this UCQ pairs, it's unreliable connection queue pairs. So you can have much better scalability than the reliable connection queue pairs used by Nico. And then among these 200 queue pairs, we will do some load-aware packet spree. You can think of, we will pick a path based on like whether this path has lowest latency in the last time, If it has lowest latency, we will send packet using that path. So in the hope that that path won't hit congestion in this round. And the next time we will pick another path so that we can split the big data into smaller chunks, and each chunk will get transmitted. We will likely go through different network passes to avoid the network congestion. Yeah. This is just a slide that for some RDMA expert, you may know that this Q pair, these basic the connections on RDMAs will consume some RDMA NIC hardware resources. So it's true. We tested for different Q pairs, different types of Q pairs. For example, for reliable Q pairs, commonly using nickel, and also for unreliable Q pairs that we use. We found that it's actually not that severe if you even it will not incur very, very high performance drop, even if you use 60K Q pairs. The reason is because it's unique to the ML workload where you just send really, really huge data. And the major cost is because of data sending, but not because of other like metadata or Q pair incurred PCIe transaction overhead. So you will see that with relatively large data size, we nearly have no performance cost even using a lot of Q pairs. And that especially is true for UC Q pairs, these unreliable connection Q pairs that we're using in our UCCL collective communication library.
Before that,
is
there any
Is that too technical or? Okay. Let me think of.
Yeah, I think that MOE is like so the key challenge of MOE is on networking. Like in the forwarding path, like the MOE communication roughly occupies currently 50% of the time. So communication is the bottleneck. And Yang's work is exactly optimizing for that.
Okay, so I guess for this part, it's basically you have different type of NIC vendors. They support different type of connections. So we have a suite of solution to work for different NIC vendors. But here we can just skip it, I guess. Maybe we can to the next two slides, I guess. Okay, yeah. Let's basically summarize how we do how we decouple this. We basically leverage these hardware primitives to decouple the control and data paths. The next challenge is how do we gonna achieve really high performance? It's all related to how we're gonna build our system, how we're gonna architect our system to avoid any software overhead on the critical path. What we did is you can look at the left part. That's the application thread. You may run some PyTorch, Python thread or process, and we will call the collective library. Right now, you can just call Nico collective libraries, and behind these Nico library layers, it will link to our UCCL plugin layers. It's basically just you need to override a environment variable. You do not need to change any of the Nico code or your application code. It's just one-time environment variable change. And then this Nico plugin will communicate with a set of UCCL engines. Each engine will be just a thread that is a run to completion model. We will not do any, for example, context switching between these threads. Each thread just dedicatedly run on that call. And it will do three types of actions, but transmit the data and receive the data, and also doing some timeout or pacer to maintain the reliable delivery of the data because we're using unreliable connections. We start. Yeah, we'll not end here. Yeah. But of course, if you want to do really fine-grained control on every packet, you basically make control decisions. For example, load balancing for each packet is gonna be still really costly. So what we did, one core technique we did is we try to coalesce multiple packets into a bigger chunks and only make control decisions for that bigger chunks. You can think of if a single packet inside that chunk lost, that the big chunk will just drop by us, and we will retransmit that big chunk. Yeah, of course, many other optimizations, but it's mostly about how we're gonna. Yeah, go ahead. Uh, you mean the data will get transferred? Yeah, it depends on the workloads. For example, if you're doing training workloads, normally the gradients that goes through the network, you may cause some or reduce your maybe model weights, something like that. It could be all kinds of data. Yeah. Mm-hmm. I see. Yeah, I believe for many applications, they have done this optimization at the application level. For example, if you have some model weights and that will get changed over time, you just cache it in local SSD or in local host RAM or even in the GPU RAM. So what we did here is for everything that you want to communicate between different GPUs, you will go through the NICO layer, the NVIDIA collective communication layers, and we will accelerate that part of transfer. Yeah, yeah. Mm-hmm. Uh, uh-huh. It's definitely possible because that's why in the later we can see some performance gain. That's exactly because some transfer they collide on the same network path, so that their performance will drop severely, basically get half, right? And that's why we can see some performance gains in the later. Yes, we definitely see that case. Yeah, yeah. Yes. Uh-huh. Yeah. Yeah, we just gave it to the network hardware. Normally nowadays, data center they use ECMP equal. I couldn't remember the specific name, but what they did is they will do a hash function, maybe on the packet 5 tuple, so that as long as these 5 tuple normally embed the QP number, source QP and destination QPs, as long as you have different QP numbers, QP pairs, they will basically go through different paths. Yeah, that's a hidden assumption in our work. Yeah. Yeah. Oh, that's a good question. We have, because of going multi-pass, that's actually one of the things we cover in the paper that because we do everything in software, you can easily handle packet reordering by maintaining basically a C++ STD map, and you map your sequence number to the right packet pointer. There's no, because you are doing everything in software, you have enough memory, you can store arbitrary out of order packets. That's one advantage where we have compared to the hardware-based RDMA approach. Yeah. Okay. Maybe we can go to the next slides. Yeah. Next few slides gonna be about what's the time now? It will be about implementations and also evaluations. There might be some interesting evaluation numbers. But before that, we'll go through our implementation. We support many features. Perhaps the most important one is it's a plug and play. It's a drop-in replacement for any NICO applications. What you need to write is just write a LD preload and specify our library with your PyTorch or Python or applications, and that's it. You can run with our library. The other three are some fancy networking specific features for this RDMA transport. Typically you will see that in some NSDI or SICOM papers, especially SICOM papers. We can do packet spree, we can do latency-based congestion control, receiver-driven congestion control. We can tolerate up to 5%, for example, 5% of packet loss, you can still get a 90% of throughput. You basically do not need all kinds of fancy techniques that was done by NVIDIA's networking team. It support both NVIDIA, we mentioned before, it support both NVIDIA AMD GPUs and a lot of NIC vendors. We're right now actually working with AMD plus Broadcom NICs to enable large-scale expert parallelism on their GPUs. Okay, maybe go to the next slide. Okay. Finally, we're having some evaluation results, and I hope this figure is easy to understand. Maybe we basically got 6 HGX servers, each with 8 H100 GPUs, and also each with 8 400G NVIDIA CX7 NICs. That's basically at that time was the most advanced testbed. And of course, it was donated by some industry collaborators we can use only for 1 week. And their cross-rack Rocky architecture. Rocky is one type of RDMA fabric that is typically seen in some large-scale companies, large-scale deployment. And we run this standard NICO test or reduce test. We try to increase the data size in the x-axis, and y-axis is the bus bandwidth you achieved with UCO or NICO. You will see that it's very interesting that NICO will have some performance collapse at different time point. For example, at this 256 megabyte, you will see the bus bandwidth drop severely. Yeah, the reason is because these they collide on the same path. If a two-stream 400G flow collide on the same 400G link, they will compete with each other, so that each one only at most each one get 200G, right? But the truth is that this congestion control will do some exponential back off, so that you will get they will preactively self-limiting itself. Yeah, yeah, yeah. They will just try to reduce their rate exponentially. Yeah, there's some problems. But we can do something called packet spree, so we can go different many passes, and we can tolerate some kind of delays as long as it doesn't impact the overall latency. That's why we can get a better performance than the existing NICO. Maybe go to the next slide. Oh yeah, this is a figure we done with AMD's hardware. Previously, the previous figure is done with all NVIDIA's hardware, NVIDIA GPU plus NVIDIA NIC. Now it's AMD's GPU plus Broadcom NIC. And you can see we observe very similar patterns, no matter what their architecture is. They actually use something called a re-optimization that help reduce some network congestion. But still, you can see the RICO. RICO is basically a AMD version of NICO. They will hit some network congestions, and we can outperform it much better. And we actually already reach the line rate, this 50 gigabytes per second. This is for the auto workload, so you can see the number is slightly lower than the previous or reduced workload. Yeah, yeah.
What's the typical data size?
It's typical dozens of megabyte. But it all depends on the model size and also the battery size you set. But in the next slide, that's about our Megatron training LM. I think it's roughly about dozens of megabyte. Yeah.
So it's like
16 to 256. That's a pretty common pattern.
So it's like first case of like this RCCL.
You can think so, but not. But the problem is, not all their message are at that range. They have some small message, but only the large message will dominate their performance. Yeah. Mm-hmm. So can you see again? You mean compare with? Mm-hmm. Uh-huh. Oh, I see. That's it's a fair because we use, for example, for this one, although we said we're UCO, it's actually UCO plus RICO. So we didn't change any code in RICO. What we did is we let RICO link to our network plugin library, so it directly goes through our layers without any code change. Yeah. Yeah. It's just how we handle this network congestion. Yes. Yeah, we have no control on the NIC and the switch, so there should be the default the same. Yeah. Okay, maybe we can go to the next slides. This slide is on the same hardware for AMD servers. We run they have a tool called a Primus, but basically a wrapper for Megatron LM, so you can run on AMD devices. We run a EP32 on 4x8 GPUs. We see some performance gains, not big, but still like up to 8%. I would see we have like 64 experts, and this performance number is gotten without any single line of application code change. It just specify several environmental variables and run your PyTorch Megatron LM application. You can get these performance gains. And
is it per GPU number?
Yeah, this is average tokens per GPU, but you can just time it by 32. Oh, this is a Rico. It's AMD hardware. Yeah. This is a DeepSeek V2 Lite. Yeah. We're experimenting with V3 and also expanding to more servers.
Just in the background, the DeepSeek V3, the large one, this is training. It's a different story.
Yeah, it's training.
But the average number of tokens per second per GPU is around 2,000 to 3,000. So that's
yeah. This is not Infra. Yeah, it's training. Yeah, and also like not V3, it's V2. Yeah. Go ahead. That's a good question. We do increase the CPU load. We actually get questioned when we submit to SSP. Finally, we didn't get in, but they are wondering about the CPU load of typical training jobs or inference jobs. We get some numbers, not extensively, from some GPU vendors. They said their internal training team only see like, I think it's 14% of CPU utilizations during their training. 14%. The reason because they have hundreds of CPU cores on a typical GPU servers. It's basically 200 or even 300 number of CPU cores. So we think right now in our paper we use 4 CPU cores per each GPU. You can also use 2 CPU cores for each GPUs. We actually test they are have pretty similar performance.
That sounds big because so it's typically the CPU actively launching the kernels. So if you add load CPU basically
but they are actually running on different CPU cores. Yeah. We basically in our code we'll try to ping them to different NUMA node, and then they will not interfere with each other. Yeah, that also done by Nico because Nico itself need to consume CPU cores.
So the assumption CPU is relatively not that constrained resource.
Yeah, I would think so because if you look at the price, one GPU might be worth of the CPU plus the whole DRAM. So if you can just burn some CPU cores, burn some DRAM spaces for 10% or 9%, 8% of speed up, I would think that's pretty useful.
So true, yeah. Still like the media currently is like packaging their servers into a whole box. Which will higher end.
Yeah, they're relatively fixed, but they're actually pretty big, still pretty beefy. Yeah, they have like 144 cores. Yeah.
Like the situation where the routing cannot work and also the congestion control cannot make any normal that like how much over can have on the
You mean do we stress test ours?
with your
under
the situation that your algorithm does not have any benefit.
Oh, I'm not sure if I could exactly answer your question because we actually found CC doesn't matter too much once you have multipass. And finally, in our any version, we compare in our paper. We compare when you have some very dumb TCP cubic CC, or you have very advanced Google style of Swift latency based CC. It makes no difference as long as you can increase your pass to 256. everything about CC doesn't matter. The only thing about the matter is the load aware load balancing or the multipass. Yeah.
Like, since you're multipassing, will it wear out the NIC more quickly?
Where what? Sorry.
Wear out like the NIC, like die quickly.
Oh,
yeah, doing hardware damage.
good question.
If you wear out your hardware 256x faster, then it doesn't solve.
I haven't done any. Yeah, it's really hard to know. Yeah, but I know some storage devices will have these wearing out issues. But for networking, I haven't seen any study in this either from industry or academias. But even if they were wear out, I guess the GPU will be first to wear out. But people trying to keep their GPU cluster busy.
That's
yeah.
Also, I guess NIC is much cheaper than compared to. Yeah, we just optimize for the most expensive. Makes sense.
Yeah, exactly. Yeah, the NIC, the NIC is much cheaper actually, but the data center fabric is not cheaper. That's yeah. Mm-hmm. Oh yes, that's yeah.
It will just cause a slide of policy.
That's true. Yeah. Cool. Maybe we can jump to the next slides. Okay, this is still a boring evaluation slides, but when I got this result, I got really shocked that why AWS NIC is so poor. So we still do not have too much understanding on why they are so poor. The reason I choose it because I do not have IB testbed, so I got some AWS P4D servers, basically A100 servers, and now I try to support them to see if we can get performance gains. Yeah, we still do not have a reason, but the hunch is that their NIC is built by themselves, and this seems run some software on their NIC is running on their ARM cores. So in our paper, we try to see that because from past smart NIC papers that using ARM cores, they claim their performance is normally much poor, much lower than the normal x86 CPUs. So we think that might be the reason. Yeah, maybe we can go next slide. Okay, that's all about our evaluation. Maybe we can show quickly about the roadmap. What I have present is about a better networking abstraction layer to make the transport layer extensible to get higher performance by adapting itself to different workloads. UCCL has been involved to beyond this just simple just pure networking layer things. We'll try to working on in the upper layers. For example, can we make NICO better? Can we improve the NICO's performance by making their CPU part more efficient? If you run NICO, you will know that you see that they are actually consuming some CPU cores, usually 2 CPU cores per GPU. We try to make that part more efficient. And also NICO will consume some GPU SMs. These SM are actually pretty expensive. To give you a number, if you run H100 with 400 NICs, you are likely to have 16 to 32 SMs devoted for this NICO communication. That's already probably 1/4 or 1/8 of your total GPU's SMs. So you want to make that SM free so that when you do collective communications, you do not need burn any GPU SMs. But of course, only for some copy-only collectives.
You're just wondering like that, right? Require you to rewrite the.
It won't affect the kernel rewriting part, because NICO is totally issued by the CPU. But we need to rewrite the NICO kernel. That's true. Yeah. Okay. Of course, everything right now is in Triton. Triton is really popular. We want to wrap the NICO's device kernel into Triton language to support different devices. For example, AMD's CCL called Rico without just rewriting the kernel again. After the collective layers, we're actually building, for example, we're building some better transfer engine for KV cache transfer, and also for this RL post-training with broadcasting. We basically want to see that can we achieve better performance than Nico, and even and also for Nixel. For Nico, we already achieved really much better performance. I was showing the last two slides. We're still trying to competing with Nixel. If we can achieve even better performance than that. The third big direction is on the MOE, all-to-all communication patterns. We try to make it generic. Right now, if you want to run IBGDA, you need NVIDIA's GPU plus NVIDIA's networking, NVIDIA's network devices. I'm not saying NVIDIA is doing wrong, it's just that's their company's business. They need to drive that direction. But as open source developers, we want to run on heterogeneous set of devices. For example, AMD GPUs plus AWS EFA NIC and Broadcom NICs. And of course, because these vendors support us, so we want to make that work. Yeah, we want to hear about your feature needs, especially from production needs, or some thoughts that you think it should be worth adding to the collective library or adding GPU communication libraries. Maybe next slide, a little bit more. Maybe the next slide, yes. Yeah, here is our early results on the P2P engine I just mentioned in the last few slides. We try to compare with different P2P engines. We try to vary their message size and transfer this message size from GPU A to GPU B across RDMA networks, and we'll compare their throughput. The biggest lesson here is, there are two lessons. The first is Nico or Rico is actually not that perfect for KV cache transfer. The second is, if you're using Mooncake, probably Mooncake is not saturating your line rate. That's another problems we found when we tried benchmarking the Mooncake transport engine. So far, we can achieve very similar performance with Nixel, but we'll see if we can continuously optimize it. Maybe next slide. I think that's the last slide. Yes, this is the last slide. The theme is we want to build a ultra and unified collective libraries, not only collective libraries, but also general GPU communications. We're open sourced. The paper is here, and thank you. Yep. Yes.
YouTube live.
Oh yeah.
You can repeat the question and answer it.
Okay, yeah, sure.
Hope you guys still remember my face. I'm the guy who opened the door downstairs.
Okay, the question is, there are two questions. The first is, did we do the packet reordering in CPU, and what is that speed? Did we do that reordering, then pass it to the GPU? So for that question, no, we actually, it depends on if we are using UC, the unreliable connection. It allows you to directly write data from your source GPU to destination GPU. And in the source CPU side, you can specify that destination GPU address. So we'll directly write there. There's no reordering issue for that case. But of course, we also support AWS EFA NIC that does not support unreliable connection. In that case, what we did is we modify the Nico kernel to do packet reordering inside the Nico kernel that has already used by Nico. We just add some more logic there. So we has not compared with the second question about whether we compare with hardware-based packet sprees. I think we did not get any hardware. We did not have any testbed that support this hardware-based packet spree. That's one reason we could not do that experiment. But I believe it has some problem, because I know when they do packet spree, they need to issue some extra options to make sure that the order is guaranteed. We talked with some ByteDance people, their production teams. They said their packet spree doesn't help them much, but we haven't tested, so we do not know the answer. Yeah. But the slightly point is the hardware-based packet spray has very bad limitation that you can only do you cannot send too much in-flight bytes because their hardware has some space limitations, and you will require some PFC to make sure that your network is lossless. So we think that's actually not good for the today's large scale deployment. Yep. Oh yes. Uh-huh. Mm-hmm. Mm-hmm. Mm. Yeah. Mm-hmm. 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 Yes, yes. It's true. The CPU consumption, because in CPU world, CPU is expensive, and also memory. We didn't consume too much memory. That's okay. Another thing is in the traditional CPU world, we didn't see too much network problems. Reason because their workload is not too bursty. They're not like Wang's applications using the 400 NIC for like 10 seconds. They're just using that NIC maybe for very few microseconds. So they are normally do not have too much network congestion issues. But in ML, it's different. So I would say we will not have benefits if we apply to non-ML, non-GPU world. Yeah, it's important. We tested. We actually also tested on small. The small is there's no congestion issues. You can easily send everything. We do test our software implementations, and for small message, we didn't increase their latency by much. Probably if you see one small message might be 60 microsecond, we will increase it to maybe 65 or sometimes even lower. It basically for small message, we done some optimization in the transport layer to make sure that it doesn't get too much performance slowdown. Yeah. Maybe. Oh, really? Oh, really? Okay, I'm scared. Oh, yes. Uh-huh. Yeah. So PD discretion is for inference. And we're doing some better transfer engine, faster transfer engine for that. Another is I know if you run some Kimi models, they might do some TP16 that cross two nodes where the network is really important. So we might help on that aspect, especially if that two nodes are across different racks. We might help on that because we tested on across different, even two nodes across two racks, there will be some network congestion issues.
Also for those very large scale MOE models, like for example, DeepSeek V3, there's a good way to service is using very large scale DPEP setup. For example, EP128 that requires 16 different physical nodes of H100s. And I think that under that situation, when we are doing like MOE stuff, there is a all-to-all communications.
Yes,
and
yes.
which will be, I think, will be very useful to probably try use UCCL.
Yes, so we're actually working with that. We're working on integrating DBP into different types of hardware like AMD GPUs, AWS EFA NICs, and Broadcom NICs. We're working on that direction. But we're also having some emerging use case is a sequence paradigm where you do some send and receive in a ring pattern. And one of my colleagues at Berkeley, they run this large scale sequence parallelism communication on some Azure, I think Azure H100 InfiniBand node. They observe really, really poor performance. We're also working with that to, I guess it's some networking performance issues. We're working with them to fix that. Yeah. Yeah.
How would you say that your technique will fit into the NVL hardware?
Hard. It's really hard because I know NVIDIA's strategy is they try to push all their engineers to NVLink domains, multi-node NVLink. They have done many optimizations there. And the most important thing or the most challenging thing for open source or non-NVIDIA people is their hardware is typically really opaque and hidden. They didn't release, for example, what's a registry address for to accessing these features. You can only reverse engineer from their Nico code base, but normally their latest feature may not be available to you to use. So it's really hard to beat IOC on this NVLink domain when competing with NVIDIA's or even competing with AMD. But I see the hyperscalers, they are more willing to see smaller NVLink domains to have better fault tolerance, to connect them through RoCE InfiniBand or these RDMA networks, which are more open compared to the NVLink. Yeah.
Okay, that's all questions from the audience and also from like, is there any question from what's the difference with LMCache?
Oh, Nixel. Yeah. So we provide a P2P library that target Nixel's use case. Beyond that, we also provide collective APIs. And one collective API we build is we want to build SM-free collective APIs that is beyond this peer-to-peer transfer. For this, we haven't seen any performance differences because peer-to-peer transfer is purely a simple wrapper for RDMA operations. There's really hard to further improve. But what we have been doing is we try to add some algorithm, some compression algorithm into the transport engine. And that compression is lossless compression so that we can improve the throughput beyond the hardware limit. For example, you have a 50G link, we can transfer with 60 gigabyte of 60 gigabyte per second speed by doing some lossless compression on the GPUs. Yep.
I guess that's all questions from the audience. Okay. Sorry. You're talking. Okay. Yeah. Yeah, I guess that's all questions like from the audience and also from the internet. Let's thank Joe for his great talk. It's very impressive. Yeah. Networking is known to be challenging and hard, and Joe nailed it. Yeah, thanks. Yeah. Okay, and let me check the time real quick. Okay, now we are 1 hour after that. Yeah. So this will be the first part of our meetup today, of our meetup. So basically the first part will be about the UCO transportation. The next part will be hosted by Yihua and I. So it will be more application. It will be more at application level, but still it won't be like at high level as agent because our agent speaker Tina is not here today, but it will still be more application stuff. Yeah. So the first thing we want to show is the quick demo, like by combining LMCache and LangGraph. Just as a background, so basically, LangGraph is currently the sort of the de facto library for agentic people to develop their application, because LangGraph is very, I guess mainly because LangGraph provide a very cool visualization and all kinds of like different agents. So basically, and by having LMCache into it, we managed to have a much faster agentic workload generation by LMCache caching policy, KV cache caching policy. And we have a quick demo here. And are we ready to show it, Yihua?
So, but before that, I can briefly explain a few words about LMCache. So, LMCache is actually our open source project, building a level under the survey engine. So basically, what we're doing is caching all those KV caches for different requests to reuse, and which is specifically very useful in the agentic workloads. So, for example, in those coding agents, when we are using, like, for example, cursor or cloud code, we will usually have a quite long like context input context, because we're the agent is actually browsing through our code base and trying to build some context based on our code base. And when they do different actions round by round, the chatting history plus the action history plus their syncing will keep adding to this context. And we did some measurement. It shows that using some like open source coding agents is easily to get to, let's say 100K of the context across tons of agent actions. So when we're if you guys like, for example, if we are going to serve some like coding agent or agentic workload, usually the GPU memory, it will be not enough to save the KV cache. And also the CPU memory could also not be enough, because think about this, for the latest NVIDIA B200 machines, the CPU memory is just around 2 TB, but the GPU memory is also around 1.5 TB. So they're basically at the same scale. And if the GPU memory is not enough to store the KV cache, the CPU memory will also not be enough. And what LMCache does is it enables very fast like KV cache offloading from GPU to CPU and to the storage devices beyond GPU. For example, the local disk, where you can get around 20 terabytes of the NVMe disk on the single B200 box, and also probably some remote storage inside the cluster, like based on the RDMA transfers. Or maybe probably we can you can also store a KV cache on S3. Previously we thought it's impossible, but actually it's doable, and the performance is pretty decent. And that's a high-level idea of the LMCache, basically KV caching layer for the serving engines, and to use this use techniques that can speed up the LM inference and all for multiple different workloads. And that's a basic background. So yeah, should we do this quick demo? Oh yeah, any questions for probably LMCache? Yeah, please.
I was surprised that
Yeah, so this is really a good question. So previously we saw, okay, the GPU to CPU, the PCIe bandwidth is like say 50 or 60 GB per second, but usually SSD is just 2 or 3 GB per second in terms of the speed. However, think about this: when we are running LM inference, the prefill speed, like the speed of large language model to generate KV cache, it's actually much lower than the speed of GPU to CPU link. So for example, if we are running let's say Llama model, right? Llama model, the speed is actually what we measure is around 3 to 5 gigabyte per second, which is just on par with the speed of the SSD. So if we want to load the KV cache from SSD to GPU, the speed in terms of latency, loading time, or the latency, it will be pretty similar to the GPU. But the benefit is that you're actually saving the GPU cycles by just skipping the prefill. And those GPU cycles can be used to decode to make sure that you can serve a larger workload, or your generation can be faster.
And also, just want to.
No.
Okay.
Probably I need to go here.
Yeah, let's. Okay. Yeah. So another thing is that at a high level, like what the trend that we observe is that first, like there's more and more tokens to be incorporated by the inference engine in general. Like the context size is getting larger and larger. For example, in Cursor, like they have like millions of tokens they want to store for their like tokens for their code generation application. But the second thing that we're observing is that the KV cache for each single token is getting smaller. Yep. And this is enabled by latest attention technique like MLA, and also
Sliding window attention.
yeah, sliding window attention like makes the KV cache like they even drop some KV cache for long context inference. So the second trend will be that the KV cache size for the single token will getting smaller, and this trend is not stopping yet. We will expect that the KV cache will be smaller and smaller. And given that currently, even at now, the KV cache generation speed at GPU roughly matches the SSD speed, So we expect that in the future, like this offloading will be even more feasible, even more beneficial and feasible. Yeah. So I guess that's the main two trends that kind of like motivating us to consider storing KV cache outside CPU, outside GPU, outside memory, like into a more like physical persistent, in a more physical persistent way. Yeah. Yeah. Imagine that maybe in the future you want to like for example, in the future, your KV cache from the customer is like stored on one cloud, but maybe second day you find another cloud is cheaper. You want to migrate the KV cache from a storage to another storage. Like imagine that we're doing that. Yeah. Okay. Are there any other questions from the audience about LMCache? And yeah.
I think it's just a single digit gigabyte per second, that level. Yeah, yeah.
Yeah. Are there any other questions from the audience? So for smaller context lengths, I guess the improvement will remain similar. The reason is that the KV cache generation speed, or let me say this way. So maybe the KV cache generation speed, depending on the pre-filling speed, and pre-filling speed, the pre-filling time, the pre-filling time is roughly proportional to the input length at a reasonable input context length. So in that case, since it's linear, like the KV cache that you transfer scales linearly with respect to a number of tokens. So basically, in terms of if you consider if you consider the generation throughput, it will be the same, regardless of the context. Does that make sense to you?
How do you know it's going to be for other cases, maybe for the coding, maybe you can get the whole. How do you know that something should be another way of this?
Yeah, this is a very interesting question. So I think right now we are supporting two different modes. The one mode is like totally invisible to the application users. So basically, we are using the prefix caching semantics to automatically match the prefix and do the best effort caching. And we also have some extra optimization that can detecting and reusing those non-prefix caches, but this is a more advanced feature. This is first is invisible to users. And we also provide some kind of interfaces for users to explicitly cache some, let's say, documents or the context where the user will specify, okay, this part is really, really important. I'm going to reuse it very frequently. So please store it in very fast storage, for example, GPU or CPU memory. And we can also do that so that you have the very explicit management to the KV caches in your system. So that is what we also support, because think about this right now. If you're just talking to the serving engine, the KV cache is totally behind the serving engine and you cannot control them. But if the upper level application layer can do some control to the KV cache and use some, let's say, token level or context level programming interface to manipulating those KV caching behavior, it will like probably have another room for the improvement in terms of the system's efficiency.
Yeah. So yeah, just want to clarify. So at a high level, in large language models, as long as one request is a prefix of another request, they can share the computation. So in that case, that basically imagine that maybe your next query is appending to the history of your previous query. In that case, the computation can be simply reused. And that's kind of like the agent developer 101. If you develop an agent in a conversational way where you are appending your new input to the previous output, then you will be able to reuse the computation. And most of existing agent developers start to be aware of and also utilize that.
So the question.
Pass on our chat with we see the generation as a Infra question. I get an average 0.5 to 0.8 seconds. You guys get a number for if I save my cache into maybe either this, what's the time to run?
Can you give us the size of your KB cache?
Yeah.
So can you run it?
I think it's regardless the KB cache size, but in general, if you're storing the KB cache inside, let's say CPU. Oh, for example, not in CPU. Let's start with GPU. So if the KB cache is already in GPU, the large language model can directly skip prefill, which is you cost 0 time. And in general, if you start loading your KB cache from CPU, you are actually comparing the speed of like prefill, like say prefill can populate KB cache at the speed of 3 GB per second, but the CPU to GPU memory bandwidth is actually 30 GB per second. So in terms of based on that, you actually got a 10x speed improvement for a very wide spectrum of the context length.
At one point, Falco will come to have a summary. I just want to know, did you guys compare what's the summarize and full context
So just to clarify a little bit, what do you mean by the full text answer? Mm-hmm. I see. So from what we observed that cloud by doing this, Cloud Code is actually trying to compress the previous context without and trying to achieve a let's say still pretty good generation quality. So this is a way. Let me explain like this. The context, you cannot let the context grow infinitely because the large language model, they have the maximum context window limitation. And if your context is really, really long, it will be also pretty expensive for the serving engines to run the inference. So in that way, those coding agent developers are trying to do one thing, that they're going to squeeze the context a little bit, probably not a little bit, but squeeze the context into a shorter one after the context has reached a certain kind of threshold. So this is actually the default behavior of the many different coding applications we observed. And in terms of the impact on the quality, I think 2 ways to think about this. So comparing to the full text, it's definitely losing some information, right? So probably for some very detailed stuff, it will be a little bit worse than you just using the full text. However, by squeezing the context, it can make the if this squeezing is doing in a very smart way, let's say it keeps most of the important information, it can help the large language model to be more focused on the very important information, and probably it can improve some of the quality by doing that. Yeah, so that's my understanding. Kunde, do you have anything you want to say?
Yeah, just want to like answer this question. So basically, you're saying that compared to generating the new code using full history versus using a compressed version of history, which one is better? My answer is that it's hard to tell. So it really depends. It really depends on your benchmark result. I can see both can happen. So basically, if the summarization kind of like it sacrifices some information, like it just compresses out some information. But given that the model, like especially in the popular model, they use sliding windows, they will drop information by themselves. So given that, if your summarization kind of like helps the model to stay focused on the important information, it might be beneficial. Yeah, but then in that case, it really depends. It depends on like the length of your context. It depends on like how do you filter your context. Are you filter it using a more aware way, or using a more like just the random context, the chunking way? So like every design choice you make in the context compression algorithm might change the result. Yeah. It just command and argument change.
Yeah, so basically, to application developers or to the users that use VLM's interface, there's no code change needed.
You just change the way of launching VLM, change the command and arguments there.
Yeah, so if you're doing some engineering, for example, you have a customized version of VLM, you have some local customization in VLM. I think LMCache can still be supported if you're using a very the recent versions of VLM, because we do have a interface that's put already into the upstream VLM since I think it's VLM's version 0.6 or something, like half a year ago, probably. And by using that upstream interface, we can directly we can always be compatible with the latest VLM versions. And if the code change you have inside VLM does not touch that part, I think it should be still compatible.
Yes, as long as you are regularly updating your own VLM code with upstream VLM code, it will be compatible.
How about ST-Long?
Oh, we do have the integration with ST-Long, and there is already a PR and should be merged very soon, like just this in this week's. Yeah. Oh. Okay, very good questions. So first of all, the request routing, I think there are two things. One is if you're only saving the KV cache locally to each VLM instance, then the request routing will be pretty useful, because you can, in the router, you can detect which VLM instance has the KV cache you want. But LMCache also supports that you can share different KV caches, share the KV cache across many different VLM instances. And if we have that, the request routing is will still be useful, but it's, I would say, less critical to have the performance benefits. Yeah. And to the second question, so LMCache is a purely open source project, and we have a lot of like community contributors from different communities, including like from different industry partners, and also a lot of like university students. So I think the project itself will remain open source. It's using Apache license. Yeah. And in terms of making money, I think since we are also a startup and we are trying to see if there is any like opportunities to build some very useful like product based on this, not directly using this, but based on this to make people like better utilize or managing their KV caches. That could be probably a chance. But yeah, hope that answers your question.
For example, if you want to customize LMCache according to your own cluster need, then you can reach out to us. Yeah.
Happy to help. Yeah, please.
But actually, I think cache for KV cache. But for the long chain use case, I think the most of the time for use it to what is it to be cached? The prompt the different the prompt to the how LM can be so different What the difference between why is cache for each
you want to answer?
Yeah. So basically, like the KV cache optimization that we're done is transparent. Transparent means that as long as like the user send us 2 queries and 1 query is other queries prefix, we can help them reuse the computation. And we found that kind of like pattern where the future query is kind of like appending to previous queries to the answer of the previous query. We find that the pattern really common in agentic workload. For example, assuming that maybe 2 agents are conversationing with each other, then the second agent will naturally use the first agent's output as input. And in that case, we can reuse that part of KV cache. We can help them save the computation of the first agent's output by reusing that part of KV cache. So even though like our optimization is transparent to users, since we observe that agentic workload, they kind of like just naturally the conversation with each other, they kind of like in general referring to the same context pretty often, we can still observe speedups from by our caching service. Does that answer your question or?
services. So if we're wondering how the LMCache to use it.
Oh.
Very good question. Actually, this one is LMCache fast LangGraph demo. So we are also trying to build some kind of like serving engine endpoints. Which behind that we deploy VLM plus LMCache as a serving engine. So I think in this demo we are actually connecting LangGraph to that endpoint we host, so that people can directly get benefits from the latest open source technologies.
Separate like
Oh, good question. So I think you can treat LMCache as a centralized storage layer where you can store all your KV caches centrally, and LMCache itself can do some kind of management. For example, if you're using different models, of course your KV cache are different, so that LMCache will be able to find the correct KV cache for each model. And but if all the models, basically you're running multiple serving engine instances with the same model on multiple clusters, you can share the same LMCache backend where you store all the KV cache in a centralized way.
So as long as like
Yeah, I saw that guy has a yeah. You want to answer this? Okay. Good question. So this is really we observe many similar use cases where in the system prompt probably you have to embed something like the current timestamp or some meta information that is going to be changed frequently. And what we have is we previously have a academic paper. It's actually the best paper of the UCCL this year, called Cache Blend, where even the technology itself enables you to reuse the most part of the KV cache of the document, even though the prefix, the first field token has been changed. So basically the technology itself, technically it's actually any part of your prompt is reused, it can reuse the KV cache.
Yeah, but it's like we'll support it in the future. This current version of demo doesn't support that.
Yeah, but in the open source LMCache repo, if you go there is some examples of cache blend that can let you to especially like for the RAG use cases, they're useful because for RAG use cases, you're loading the same set of the trunks, but for each query, they may be loading different trunks. But if you have the KV cache for all those trunks, you can directly load those trunks and combine those KV caches together to get the pretty good quality during the inference. Now, yeah, please. Yeah, I think local SSD is right now become previously is basically CPU memory is the most popular one, that's for sure. And we are observe emerging use case for local SSD because like people are realizing that okay, we have all those like very fancy boxes and in the boxes there a lot of SSD memory, SSD space, we are just not using it. So people are trying to start using that. Yeah. Yeah, for remote, it's more related to if you want to have a very large scale deployment, you want to share across your the whole cluster or even across different clusters that will start to have more like become more useful.
And the immediate need for sharing KV caches like across nodes is for fault tolerance.
Oh yeah, that's also like persistent the KV cache, so that when this node dies, you can directly resume the request on different like alive nodes.
Yeah, so basically if the current session dies, then we can seamlessly migrating the session to another node by just copy pasting the KV cache. Yeah. Yeah.
Yes. Yes. Yeah, so I think this really depends on the use case and the hardware environment. So
yeah, but as it is becoming popular, we start to see the trend. So basically the story is that KV cache is growing larger and larger. Previously it's like it fits into CPU memories, but now it starts to go beyond just the memory. It starts to require the storage devices to participate in order to fully store all the KV caches. That basically embeds all your customers' valuable informations. Okay, so do you want to talk about it? Like, because yeah, so basically we're showcasing a deep research demo and show that how LMCache will accelerate it. Yeah.
Yeah, so basically directly answers the question like how do we use LMCache with the latest those kind of LangGraph or those programming interfaces. So basically, what we're trying to build is something that is more like a SaaS service, but it's more like an on-prem deployment or maybe a SaaS deployment of the VLM plus LMCache, so that everyone can use it as if using use this service as if using like, for example, OpenAI or maybe like Fireworks or Together AI endpoints. So we have the pretty similar interfaces as those like model serving interfaces, and to the application developers, they're basically the same, just changing the OpenAI API URL. So this is just a very fun demo, and behind I believe is running Q130B model on a single H100 GPU. So that's just a quick demo, I guess.
In the future, we can run our demo and Together back to back.
Yeah, probably comparing, but we do have some comparisons. I believe we have some demo video, but I think it's probably too hard to dig it out. But it's just comparing the LMCache with those open source endpoints, and we can see a pretty decent like speed difference when you're streaming a large volume of requests into the same endpoint, because LMCache, you can cache the KV cache and it can save the GPU cycle so that you can spend more time in decoding and generate tokens at a faster speed. Whereas in those probably other baselines, they're just need to preview and decode the request and become like a little bit slower, much more slower actually.
And is there any other questions from the audience?
Mm-hmm. Yeah, I think so LMCache, most of the LMCache, the technologies in LMCache is focusing on like speed up the prefill, basically cut the GPU cycles needed by prefill. And speculative decoding, I would say, is quite orthogonal to the optimizations in LMCache, but we do also have some like optimizations, and we are contributing that to VLM for the speculative decoding. Yeah, and we're also using that into the if you take a look at the screen, there's a small logo called LMIgnite, which we are trying to build as a product, and there will be a beta release soon. So basically, the LMIgnite is an endpoint that integrates all our optimizations plus not only include LMCache, but also including a lot of optimizations in VLM. So yeah. No, they are orthogonal. So basically, they're addictive. Yeah, we can use both.
Yeah. Is there any other questions from the audience? Yeah. Thank you for so many questions. Yes. Yeah. Thanks for all the interest. Yeah. So now that we see the demo, let me the last part will be about it should be a lot about like our another guest speaker Qinlan's talk, but he's not coming. So it will be me sharing about some interesting stuff about using the latest GPT-OSS model to like how to use it and what's the performance of it, like etc. etc. So let me do a quick screen mirroring. I'll take over the television. Cool. So like just a brief summary of like why should you use the GPT-OSS model? First, it's from OpenAI, period. And second, yeah. So another reason is that it's a model trained with agentic workload in mind. Basically, in previous like old models, if you use, for example, Llama, you will find that to making it do a tool calling is very difficult. It kind of like it doesn't obey the instruction, and the function call is kind of like the format is wrong. But in the latest GPT-OSS model, it is trained with the agentic tool calling in mind, and even in the chain of thought, even in the thinking stage. So in that case, the GPT-OSS can typically call functions much more smoother than you thought. And yeah, and the third case is that GPT-OSS exposes a native function calling API. So it's called response API. So basically, the response API will allow you to not only do the text step completion, it will also allow you to call the function in the middle and store the states of them. So basically, by using response API, your agent will be more able to do tool calling compared to just doing chat completion things. Yeah, and so here is a so this part, like this block, will be a quick recipe about how to use VLM to deliver you the most performance of GPT-OSS on different hardwares. So basically, here is so basically GPT-OSS is a model that it's very good because it can deploy on a relatively smaller scale. DeepSeek, you need to use like 16 nodes, which anchors to like 16 times 8, 96 GPUs. But for this model, you just use one node is typically enough. So basically, here's the installation script. You can install from a pre-built will and then run the Docker image. And then on the A100 GPU, which is fairly well optimized, the thing that you need is to use these commands. And for H100 and H200, for A100, we don't need to use a tensor parallel, but for H100, H200, we start to recommend like the TP equals to 2 for both H100, H200 as the best performance trade-off point. So the performance is measured by tokens per GPU second. Yeah, and also turn on async scheduling. Async scheduling is a cool feature. It significantly reduces scheduling overhead. And for B200, you basically need to install the latest Flash Infra, which just have the Blackwell support, and also enable the good MOE implementation here in the environment variable, and then do every other things in the same. But for AMD, you need to you basically need to pull off some Docker images and then export more environment variables to make it work. Yeah, for MI300X, it's relatively well optimized. You just need to enable all these 3 environment variables to make it works for MI300X. But for MI355X, you need to enable more environment variable to make it fully utilize the kernels. And there also needs some like there needs to be some customization here. Basically, you need to turn on the full quota graph to make it happen. Yeah, and this is the cook recipe for your own GPT-OSS. Feel free to refer here to get the most performance out of your GPT-OSS model. Yeah, that will be the first part about like the GPT-OSS cooking recipe. About like you can refer to them in your own deployment and try it out. Okay, and the second part thing, the second part thing will be another GPT-OSS resource that I find to be really useful, and it's from NVIDIA. So there's a slice that is talking about GPT-OSS in TensorRT LM, and they have like very interesting, like it's pretty beefy. So basically, but this thing is public online, so you can maybe you can maybe even search it on internet and try to find it. But here I will just show some very interesting numbers. So basically here like you can, if you are not familiar with GPT-OSS, so basically here's a quick spec of GPT-OSS. I'm not sure if it's large enough for people to see it. By the way, credit to the authors here, Paulo and Jetin Galing. Yeah, thanks. Credit for the authors. Yeah, it's from a public talk, and I will try to make it large. Not sure if it's large enough. So basically, for these 2 models, the one thing to note there is that this active parameters per token is really small. So compared to DeepSeek, it's much smaller. So basically, even for the larger model, you can see the active, like even the model is 6x larger, but the active parameters per token is just even less than 2x larger. So in that case, like if you manage to run these models really cleverly, like the performance diff between these 2 models won't be really, it won't be like it won't be 6x difference. It will be just like a 2x difference at most if you run them cleverly. And also the context length is really long. So it's 128K and it's trained with like and it's a reasoning model. It's trained with like the reasoning mode in mind. Yeah. And it also uses a mixture of expert. It also uses a mixture of expert this architecture to enable the large scale server more efficient. And also it has a new tokenizer O200K harmony, which covers the much larger vocabulary compared to previous models. And but still, this model is mainly trained based on English text. So if your use case is about multilingual, then maybe this model consider it carefully. Yeah. Okay, and here's a brief breakdown of the parameter. So basically, the most part that is occupying the parameter is still the MLP layer, and the attention plus the embedded part is just occupying just a very few parameters. And in terms of the checkpoint size, you can see this checkpoint size and you can use that to decide how many disk memory you need to reserve for it. Yeah, and
Also GPU memory.
Also GPU memory. Yeah, and this model comes with native MX-FE4 MOE weights, which is basically you need to really use the good serving engine to provide the right kernel. So I use this MX-FE4 to really make the MOE much faster. Yeah, and here is some train details. Like so, basically, it's trained mostly on English text only dataset, and it has a specific focus on the STEM task, coding task, and general knowledge task. So it's best for coding agents. Not very good for chatting. Yeah, and it's trained on H100 and it's using Triton kernels in training. Yeah, because OpenAI has Triton, so it's like quite obvious. And also it's post-trained for reasoning and tool use. So basically it's post-trained with reasoning and tool use in mind. So basically most of existing large models it's just in traditional fine-tuning with human feedback. It's not fine-tuned with tool use. So basically this model will provide a much better tool use experience for you. And also you can configure the reasoning effort here. So basically you can control how long it thinks. For a simpler task, make it think shorter. For more complex task, make it think longer. And the thinking for example, if you make it think low, then maybe it will think like hundreds of tokens. But if you make it think high, then it will think about tens of thousands of tokens and even longer. So yeah, tuning this reasoning effort, and it will affect the performance. And also the evaluation, it achieves like O3/O4 mini level performance on all these tasks. So it's like it's a mini level performance, and it's still pretty good. Yeah. Sorry. Are you okay? Are there any questions? Okay. Oh. Okay. And there's a quick performance benchmark you can see. Yeah. And this is just comparing these two models back to back.
By the way, a very interesting story is when GPT-OSS released the first day, we are trying it, and we are trying the 120B model. And the first task we give it is let it to write a Python program to have a terminal like Tetris game. And it's generating that game just probably within 2 minutes. I cannot remember, but the game itself is functional and it's pretty nice. So I was pretty impressed by this model because it can run it on just within a single like 80 gigs GPU, like A100, H100, but with a pretty powerful like capability. Yeah.
Yeah, and it can even color the Tetris pieces. Yeah, so very good. Yeah, very beautiful the UI. Yeah, and so basically, this like in terms of the architecture, this model uses a sliding window plus its attention sinks. So basically, it will capture the last few tokens, but also the first few tokens about the attention sink to make it really like long context efficient without dropping too many accuracies. And it also has a softmax +1 trick, which is described in their paper. So basically, traditional softmax, you can see this part. It's just sigma exponential of all the softmax scores. But here there's a one here. So basically, it allows the model to, at least from what author claims, it will allow the model to ignore the tokens. So in previous one, even all the tokens are unimportant, it cannot ignore the token because softmax will always choose a token, will also choose a token with maximum activation. But in this formulation, if all the token has very low activation, it will allow the model to not choose any tokens. Yeah. So yeah, and the author claimed that it will resolve the outlier feedback loop problem in the quantization. Yeah, and also, yeah, here's some more here is like how to implement this +1 trick. Yeah, and also there's a quick comparison about the MX FP4 versus NV FP4. I guess it's mainly the block size is different, and also like for the MX FP4 it's not global scale, and the NV FP4 is like for FP32 per tensor global scale. I guess it's mainly for marketing for NV FP4, but let's get started. Yeah. Oh, sorry.
Yeah, we should quickly go through.
Yeah, let's quickly go through the slides. Yeah.
Probably
What's the time is
we can stop soon.
Yeah, let's stop soon. Like let me find if there's like, yeah, but yeah. So basically, here's like how do you configure a sampling parameter to make it better than human level, and you can maybe here it's just tell you how to tune the configurations, and also
I think there are some pretty interesting insights at the end of the slides, but that we can go through that. Oh, it's a little bit different than what I.
Oh, you have a different version.
Oh yeah,
Okay.
yeah, probably I saw a different version, but I think for the GPT-OSS model, the high level takeaway is if you want to run some agent development workflow locally with some minimal requirement of GPUs, you can use the GPT-OSS 120B. It's a pretty nice model and pretty powerful in like coding and math, those kind of tasks. Yeah, I think that's the most important thing, I guess.
I don't use it for like other languages except for English.
Yeah,
because it's mainly trained on that. Yeah.
Any final questions? Otherwise, we can probably call it to an end.
Are there any question from the internet?
All right. Thanks, guys. Thanks for listening to our talk.